Hi everybody, Mrs. Jensen here. Today we're going to walk through a couple of examples on how to actually transform data to achieve a more linear model and how to determine the best fit for your data, because obviously not all data is linear and a lot of data in the real world is not linear. So in AP statistics, most of the time you will just be expected to interpret models, interpret graphs that have already been transformed, and interpret computer output, but we want you to be able to actually do the transformation and understand what is happening behind the scenes. And so we are going to do a couple of examples here where you're actually transforming the data yourself and determining which model best fits the data. We're not going to select from every possible model that's out there. We're really going to focus on three, and really it's really only two, quadratic and power regression, which we treat pretty much the same because quadratic is just an example of a power model, so we really just call them power models, and then exponential regression. Okay, so one of the first steps that we can do when we're looking at the data, if you're given a table of the data, is to just look at what's happening with the y values as x changes. So as x is increasing by 1, what is happening with y? So obviously in a linear model, you have a constant rate of change, right? That's just slope. So you have, as x increases by 1, y is going to increase at the same rate, giving us a linear model. But in an exponential model, you might remember from your algebra classes that when you have exponential growth, it's the ratio of the y values has a constant rate of change. In other words, if I look at the x values and I take the second y term and divide it by the first y term, so 12 divided by 4, I get 3. And then if I go to the third y term, divide by the second y term, I also get 3. So you have a constant ratio of change in y. And that would be the same if you're talking about exponential decay, you would just have a ratio that's less than 1, so a fraction that's less than 1. If you're looking at quadratic models, which is an example of a power model, you're looking at the difference of the differences in y. So again, if you had a linear model and you were subtracting your, say, y2 minus y1 over x2 minus x1, that sounds familiar, right? That's the formula for slope. If it's a linear model, all of those differences would be the same. In a power model, we're going to get the differences, and note that the differences are increasing here. But if I look at the difference of the differences, so the second difference, you'll notice that the difference of the differences is the same. So just looking at the data before you even plot it, before you even start, that gives us a lot of hints as to which model will actually end up being best. So just some other refreshers from your algebra classes, from Algebra 1. Exponential functions, remember that's the format of y is equal to a constant, times b, the rate of growth or decay raised to an exponent, x. And then the power function is y equals a times a constant, a constant times x, the variable, as the base raised to a power. So if it's a quadratic, that power, b, is just 2. So ax squared is common quadratic, basic quadratic that you all learned in Algebra 1. So again, the two types of regressions that we're going to talk about are exponential and power. So in both cases, what you're going to do is transform your data by taking the log of either one or both variables, and then you're going to use your linear regression on the transformed data and get your linear model, get your R squared, and look at your residual plot, and then we do what we call an inverse transformation to get back to the best model to fit your data, whether it's exponential, power, or possibly even linear. Okay, so we'll start with exponential functions. So with exponential functions, a lot of times you'll be able to look at your scatter plot and see that it has somewhat curved pattern, and that you think that the data may follow an exponential pattern. Again, remember, you can look at your ratio of the change in y. So what you're going to do is you're going to transform one of the variables. And in most cases, we'll transform the log of y and leave x as is, your regular x values. And so you would write your linear equation in the form y equals a plus bx, where a is your y-intercept and b is your slope. Remember, in AP Stats, we do it backwards. So in this case, since you've transformed your y variable by taking the log of y, you would want to make sure and write log of y hat is equal to a plus bx. And then once you do that, everything else we did in the earlier part of the unit, as far as checking your residual plot, checking your R value and your R squared value, that's all the same. So to undo it at the end, if you've decided that this is the best model, or if you're given a problem where the equation is written as they're giving you right here, the log of y hat is equal to a plus bx, right here, sorry. If they're giving you that equation, then to undo it, what you're going to do is, we're using log base 10 here. So what you do is take 10 as your base and make both sides of your equation would be the power. So you can work your way back algebraically, but there's an easier way, and we're going to do it the easier way. So I'll show you that in just a second. So let's walk through a typical problem that's going to be an exponential model. So in your notes, you have this same problem, and you can follow along with it. We'll go through all the steps. So EFT machines, electronic fund transfer machines, first appeared in the 1980s, and then we give you this table of data with years and the number of transactions. So I wanted to show you this problem for a couple of reasons. One, it's very common to have time on your x-axis in years, and then values on your y-axis. A lot of times you might get some kind of error in your calculator if you try to do exponential models, whether it's a power model or just an exponential model, anything with exponents, when you're using such a large base as like 1,985 for 1985. So a lot of times what you will see is that we'll change these values to be years since 1985 or years since 1980. And that's because your calculator might give you a calculator overload error, and it just can't handle all those digits. That's all that it means. So if you have years, you can always use, you could even say years since 1900 and just use 85, 90, 91. Also, if you're checking your y values here, what's going to happen if you're looking at the change in y for your second term and your third term? The ratio is not going to be the same, but look at your x values over here. Your x is jumping 5 years in the first row to the second row, and then it goes up by 1 year after that. So just a reminder, when you're looking at the ratio, make sure that the x values are changing. The increment is the same from each x value, x1, x2, x3, and so forth. Okay, so here are 10 steps. These problems are a little bit tedious, but if you go through it step by step, it's very doable. So again, you would always want to plot your data, plot your initial data. So your years and your number of transactions in millions, you wouldn't have to show all the zeros, things like that. Then you're going to look at your ratio of your change in y. If you have a constant ratio for every change in x, then that's a good indication it might be an exponential model. So we could try that first. Step 3, we're going to do linear regression on the original data. And that's so that we have an initial r squared value as well as the residual plot to compare our new model to, our exponential model to. And then with step 5, we're going to start our transformation. So we'll take the log of y, leave our x values the same, and then we're going to graph our transformed data. So instead of x versus y, we'll make a scatter plot of x versus log of y. We're going to do the linear regression on our transformed data, not exponential regression, linear regression on the transformed data, and compare the residual plot r and r squared for our transformed model to what we had in our original model. And then if it's a better model, we can do what we call an inverse transformation or use the calculator, which is faster, to get the exponential equation, or what we call the exponential model, and show that on our scatter plot and see which one is the best fit. Okay, so we're going to go through it step by step, and what I'm doing is entering the information in my calculator, and I'm going to show you what the screens are on here without showing you all the buttons I'm pressing, because I think you know how to do that at this point. So the first thing, obviously, I'm going to enter my data in list 1 and list 2. You'll notice that I have changed the years to be years since 1900. So I started with 85, 90, and so on. And then list 2, I left as it is. And then make sure that your stat plot is turned on to graph your scatter plot. You're going to graph list 1 and list 2, and I can look at my scatter plot. And you can see it looks fairly linear, but if you notice, there's a slight curve in the pattern of data there. So when I do my linear regression on list 1 and list 2 on the original data, and I'll save it in my y1 equation just to make it easier to graph, you'll see that my r and r squared values, they're very strong, they're very high. So my correlation coefficient is 0.9695, and my coefficient of determination, r squared, is 0.93997. That's really high. So there is a strong linear tendency to this data. But is it the best model that fits the data? When I graph the least square regression line here, if I go back and just hit graph again, it's plotting my list 1, my list 2, and now the least square regression line that I just ran. You can see how it starts to kind of dip below the regression line at a certain point. And when I do the residual plot by putting in, I'm going to graph my my scatter plot, go to stat plot, and just change that list 2, change that to residual. Remember, you have to do that after you've done your regression here. And then I get my residual plot, which is hard to see because it's behind my video there. But you can see there's a pattern in the data where the points are dipping below the line here. So where those points are all on one side of the line, that's where in the residual plot it makes kind of that parabolic pattern. So again, to do the regression, remember I'm just doing stat and then go over to calculate and make sure you go down to number 8, linear regression, and then calculate. Okay, so now we're going to compare the linear regression to transformed data and see which model is a better fit. Okay, so now the transformed data, I've already looked at my ratio in the change of y, and so I think that an exponential model might be a better fit. And so what I'm going to do is go back to my list, so stat edit to get to my list, and in list 3, I'm going to highlight the top here with list 3 and type the log button down here, the log, and then do second 2, the log of list 2, and enter. And then that puts the log of my y values into list 3. So once I do that, now I'm going to do linear regression. Let me say that again, linear regression on the transformed data. So I'm doing x and log of y. So I'm doing list 1, list 3. Right? And I'm going to store that as an equation in my y2. When I do the linear regression on list 1, list 3, I end up with a new linear equation, which I would write with the predicted log of y, so hat over log y, is equal to, and then just plug in your a and your b for your y-intercept and your slope for the transformed data. So this is an example of why it's so important to define your variables, because now I'm working with x and the log of y instead of x and y. So now when I graph the data, I'm graphing list 1 and list 3, so x and the log of y, and that least square regression line on my transformed data, you can see how it's a much more linear pattern. It's a stronger linear pattern. And when I graph the residual plot, that residual plot is now much more scattered. So if I look at my r and r squared, those values went up as well. So even though they were high before, but now they're even better. So when I'm writing, you have to be careful about whether you're writing the equation for the linear equation of the transformed data, meaning you would write a linear equation for x and log y, or if you're writing the exponential equation for your exponential model. So now that I know that the exponential model is a good fit for my data, or a better fit for my data, I can go in and do exponential regression. And so what I'm going to do is go back to Stat, scroll over to Calc, and go down to 0, or number 10, and select exponential regression. I want to do exponential regression on my original data, list 1 and list 2, not list 1 and list 3. So I'm going back to my original data, list 1, list 2, and I'll store that in my Y3. And then what the calculator gives me. So let's compare the two. And most of the time you'll be asked to compare between two models. We will have one situation in a lab where we'll have you compare 3 models, the exponential and the power. But for the most part, you would compare 2 different models. So you can see the model on the left is the linear model, and then the model on the right, same data points, obviously, but the black curve going through that's my exponential equation compared to the blue line that's just the least square regression model. So clearly the black line is a better fit for the data, or the black curved model is a better fit for the data. So I want to look at my scatter plot. The second thing I want to look at is the residual plot. So the residual plot on the right is not perfect, but it's a lot better than the one on the left. So you're just going to compare the two to figure out which one is more scattered and less of a pattern. So again, the exponential model is better there. And then I can look at my R and R squared values. So the correlation coefficient and the coefficient of determination are both higher in the exponential model when we use the transformed data than they are in the linear model. So when I write the equation now for the exponential model, the exponential equation, note that it's going to be y hat is equal to, and then this 0.3804, that's my A term right there. That's the kind of the starting point, if you remember from exponential models, exponential equations. And then 1.113, that's the rate at which it's growing, right? And then x would be my exponent there. So when you do these transformations, for the exponential model, you might have to write 2 different equations. One is the linear equation for the transformed data. So you're using x and log of y hat. And then the second model is the final model, which is the actual exponential equation itself, where you're using x and y. Okay, so here's a recap of what we've done in our calculator. And again, we can show the linear equation in terms of log of y is equal to our y-intercept plus our slope times x. In our transformed model, we can compare our r-squared and our r values to what we had in our initial linear model. And we can decide that because this linear model, the transformed linear model, is a better fit than the original linear model, that tells me that the transformed model is better, and we did just the log of y, so that turns into an exponential model when we're doing our actual equation. So algebraically, we could work backwards and get our equation to be y hat is equal to 0.4486 times 1.11 raised to x. Or in our calculator, we can use the exponential function, exponential regression function on our calculator to get the exponential model using our initial x and y values. All right, so somewhat quickly here, we're going to go through one power function problem. Again, we're talking about the form y equals a times x as the base raised to an exponent b. So for power models, we're going to take the log of both x and y. And again, we could do it algebraically and all that, but we're going to let the calculator do most of the work. So in this problem with Olympic weightlifting records, we're going to look at our data. We'll go ahead and plug our data into our calculator in our list, and then we're going to do a linear regression on the original data. We're going to transform the data for both x and y. We'll take the log of x and the log of y, do a linear transformation, a linear regression equation on the transformed data. And then if that's a better model, we'll do the power regression to get the actual equation from our calculator. So similar to the exponential steps, we have several steps here. The only difference is now we're going to take the log of both x and the log of y and work with transformed data in our list 3 and our list 4. All right, so the first thing we're going to do is just graph the data straight up. Right? So put it in your calculator, list 1, list 2, and we're going to do a linear regression, so stat calc number 8, and store that in y1. I just tend to do that because it's easier to graph and plot the data. And so here's our regression equation. So again, we have really high r value, really high r squared, and even if we plot the data, it's going to look very linear. So you have to be kind of careful. If you're asked to evaluate two different models, don't just look at those numbers and say, wow, that's a great fit, I should just stop. Chances are the question will prompt you to keep going, but here you can see when we plot our data and we plot the LSRL, several of the points here are above the line, and then at the other extremes, the lower x values and the higher x values, the points are below the regression line. So there might be a better model. And so we're going to look at the residual plot, those 4 things. The residual plot definitely has a pattern to it. So now we're going to transform our data. So we're going to take the log of x and put that in list 3, and the log of y and put that in list 4. And as you can see, simply highlight the top of your list and type log and then the list that you want to take the log of, and it populates it for you. It's very quick. So now I'm going to do my linear regression. So stat calc 8 on list 3 and list 4. So this is working on my transformed data. So I'm doing the log of x and the log of y, and I'm going to store that equation and get my linear regression equation on the transformed values. So note that when I write the equation down here, this is how I would write the equation of the transformed values, right? So I have the predicted, remember with the hat, log of y is equal to 1.618 plus 0.578 times the log of x. And then compared to our initial linear regression equation, of course, there's no logs in that because I didn't transform anything. So when you're asked to write the linear equation for the transformed values, that's what it wants. It wants the log of x, log of y. And keep in mind now, if you're going to go and interpret the slope and the y-intercept based on this equation, your transformed data, you're going to have to interpret it relative to the variables that you're using. So the log of x and the log of y in your interpretation as well. So now, once again, we have to decide which model is best. And in this case, there's just really subtle differences. They're both very close. But every time you do this and compare which model is best, remember you have to look at the four things: the scatter plot, the residual plot, R, and R squared. So looking at the scatter plot, they're pretty darn close. This is on our left, the linear model, that's showing x compared versus y. And on the right side under the power model, we're comparing the log of x to the log of y. Both of them are pretty good fits for the data. The residual plot, definitely there's a pattern in the linear model. There's still kind of a pattern in the power model. And as a matter of fact, it almost looks like the same graph. But there is one little difference here. That point, whoops, and that point, it looks a little bit better in the power model, but not much. Really, just between the graphs, we wouldn't be able to tell. So you really have to look at the R and R squared values in this case, and note that the R value is slightly more for the power model down here, and the R squared is slightly higher, but just ever so slightly. They're both very close in this case. Usually it won't be that close when you're trying to make a decision. So when I'm writing the equation now for the best model, the linear equation is still a linear equation. Y equals the y-intercept plus the slope times x. And then the power model, note that at the top here, they kind of give you the form. So to get the power regression, what I do is I go back to my calculator and I hit Stat, Calc, and I go either down or up to where it says power regression, which on my calculator is A, and I hit enter. And here I'm going to use list 1 and list 2. So I'm going back to the original data, not the transformed data, when I'm going to do it for my power regression to get my actual equation. And so when I write the actual equation, now it's back to my original x and y, so I don't need logs anymore. So I have y hat is equal to a times x raised to b. So 42.443 times x raised to 0.574 roughly is the equation of my power model. So that does appear to be a slightly better model in this case, but ever so slightly. And remember, power, exponential, linear, those are 3 different regression models that we're using in this class. There are a whole bunch more that we could use that might be a slightly better model than what we picked, but we won't ask you to go through more than 3 for sure. Usually not more than 2, because you can see how much time it takes just to do that. But so given the 2 models here, linear compared to power, which model is better? Based on primarily the R and R squared, but I still want to show all 4 things, the power model is slightly a better model. Okay, so I hope that helps. Definitely if you can walk through the problem along with the video here, hopefully you were able to figure out the calculator steps and understand what the calculator is doing behind the scenes. Also note that if you do the power regression from the beginning, you will get the same equation. You'll get the same residual values, the same R and R squared as you do after you transform it. You just wouldn't be able to do the scatter plot correctly with the transformed data, the log of x, log of y, or the residual plot with the log of x and the residuals. But the shape of the residuals and your R and R squared value would be exactly the same as when you do the linear regression on the transformed data. Thank you and have a great day.